A minimum spanning tree of a graph is a tree that is formed from edges that connect the graph at the lowest possible cost. So the minimum spanning tree exists if and only if the graph G is connected, and that should make some sense because we need to be able to get to every vertex. The number of edges you end up with in a minimum spanning tree is cardinality of V minus 1. And the MST is a tree because it has no cycles. It is acyclic. It is spanning because it covers every vertex in the graph, and it is minimum because it's the lowest cost edges that connect the graph's vertices to one another. So for any spanning tree, if you add a single edge that is not in the tree, you will form a cycle. If as you're creating the tree, the edge that is added is the minimum cost edge that avoids creating a cycle, then you will be successful in building the minimum spanning tree. So we will look at two algorithms. We will look at Prim's algorithm and we'll look at Kruskal's algorithm, both of which approach this problem in very different ways, but yet yield the same result in that they produce the minimum spanning tree. Minimum spanning trees have many applications. A common example that's usually given is that of connecting multiple locations with some kind of service. For instance, let's say that we've got houses maybe spread out, and so the question is, how do we connect all of these entities, for instance, with a road, so that people can actually move out of their houses and be able to visit everyone? And so you may have something like this. It may, for instance, this is certainly a tree. It is certainly spanning, and the costs of these individual edges would dictate whether this is minimum. But this could be a minimum spanning tree where, for instance, we connect all these locations this way, and so you can get from any one location to any of the others. And what you don't want in a minimum spanning tree is something like this, because that would form a cycle, and that takes it out of the realm of being a directed acyclic graph. Another valid example is one of reducing redundant connections. So this is one where perhaps you start with a graph that may have some cycles in it, and for instance, let's imagine that this is an airline and they've fallen on hard times, and they own these 5 hubs, and they could fly across these 5 hubs however they wanted to, but now they have to reduce costs. And so we might we want to hang on to all our hubs, but we might do something along these lines. Maybe something like this, and perhaps something like this. If those are the more efficient routes, this is obviously there are no cycles, so only the squiggly lines are being kept. It certainly spans everything. It is acyclic because there's not a cycle with the thicker lines. And then the key to make this minimal is to have all these costs actually be the lowest that they can be for this particular graph that we started with. So we can start with something like this and build a minimum spanning tree, or we can take an existing graph and reduce it. Usually there's some idea here at the top where perhaps you start with the notion that you can connect everything to everything else, and then you reduce it from there based on some kind of budget, and same thing down here. So those are just examples of minimum spanning trees, and we will look at those algorithms that give us this particular product.